Most people understand basic gearing. What's shown here is a simple 6-tooth gear driving a 12-tooth gear. The ratio of the gears is 2 to 1. The small gear has 6 teeth, the big gear has 12 teeth. This means that when the small gear turns, the big gear is going to turn at half the speed the small gear is turning. The red dots on the gear allow you to track how the teeth mesh as the gear turns. Notice that after one full turn, it aligns with the black dot, and a second full turn brings it to the red. Because of the simple ratio between the two gears, the red tooth of the little gear only works against two distinct teeth of the big gear. It never is involved with any of the other teeth. A similar thing happens if we add an 18-tooth gear connected to the 12-tooth gear. For every 2 revolutions of the 18-tooth gear, the single black gear tooth only interacts with the 12 gear in 2 locations. In early industrial machines, engineers realized this effect was a cause of excessive vibration and noise, potentially damaging equipment. In this next example, I've replaced the 12-tooth gear with an 11-tooth gear, 11 being a prime number. If you watch the red dot on the small gear, it takes 11 full rotations of the small gear before it engages the same initial tooth again on the 11-tooth middle gear. Somewhere along the way, an engineer got this bright idea. This causes every single tooth of the small gear to work against every single tooth of the intermediate 11-tooth gear. This distributes the wear across all of the teeth for both sets of gears, and over time, they actually wear more evenly into each other, running smoother and quieter as the machine continues to be used. I personally learned about this many years ago. Over time, I thought about it, realized that using large numbers of prime number gears would create a system that never actually repeats itself, or at least takes an extremely long time to repeat itself. This would be interesting to use in a piece of animated art. This next system is a CAD model of a project I'm considering. It consists of 5 gears, all of which have prime number teeth, the smallest one being 17. As you look at it, you can see how the black pointers are not going to come back and point at the red dots that they were initially pointing at. This will go on for an extremely long period of time. Because of the numbers chosen and the largeness of the gears, the largest gear has 47 teeth, a prime number less than 50. The total number of revolutions for the 17-tooth gear would be required to make in order to bring this set of gears back to its original starting position is more than 3 million. Even the largest gear will need to make more than 1 million revolutions, to return to its original position at the same time as all the other gears. The next step is to combine this with the motion mechanisms for the moving parts of the piece. This will allow me to experiment and fine-tune how the whole work behaves before committing to the massive effort of physically making it, and explore ideas along the way.